Hello, Michelle F. Hello, Katie M. Hello, Maria Z. Hello, Paulina H. Hello, what just happened? Hello, Michelle Q and Emily H. and Stephanie I. and Alan L. and Yavi B. And Cheska P. With and oh my God, it's happening. Is okay. And good afternoon, Allison M. And good afternoon, Michelle F. And good afternoon, Marilyn, who I know has been here since like a long time. Thank you. Totally appreciate it. Totally noted. Wait, where was I? Good afternoon, Katie M. Good afternoon, Jada R. Afternoon, Maria Z. Good afternoon, Fariel S. Good afternoon, Victoria R. Good afternoon, Brooke L. Good afternoon, Emily H. Good afternoon, Shy D. I think if I remember. I think it's D. Okay. Okay. Anyway, good afternoon, Alan L. Good afternoon, Yavi B. Good afternoon, Paulina H. All right. That is okay. Nice to see you all. See you next week. No. All right. So let's do some physics. Quick reminder. So everybody's like I'm very impressed. I see that you guys are very on top of the homework and you are way ahead of me, which is good. But the good news of that is that we're not going to have new homework for a little while. I'm going to catch up. I'm going to catch up to the material. So if you've handed in a bunch of things and they're okay, you could take a little rest. But if you have anything to catch up on, then please do. Again, remember always, if you get anything fewer than all the points, then you wait for feedback. And you either get feedback to tell you what to do to get the rest of the points, or if you don't, you get the rest of the points, if that makes sense. So if there's nothing more that you can do right now, then you're going to get a break. But if you've gotten anything back with feedback or, well, what's happening? Or anyway, you get it. But there's no new homework for a little while. Now I want to pick up. Did I say? And other reminder. I know this whole schedule is so funny. Remember, we do have class tomorrow. Correct. I mean, correct me if I'm wrong, but I believe we have class at 12:15, like as though it were a Monday tomorrow. And I understand that for some of you, you also have like jobs and other lives, and not everybody in the world thinks that tomorrow is Monday. So I understand that. So obviously the video but it is class. Do what you can do, please. And the video and the notes will be posted, blah, blah, blah. But again, there's nothing new we will do new material. We will keep going with the material. But there's nothing new due tomorrow other than a game turn. Okay. Oh, we have class. Thank you. Oh, thank you guys. Oh, that's points right there. Thank you, Fariel. Thank you, Alan. All right. Sweet. So yes. So please come. It'll be a party. Now what we're going to do now is we're going to finish we're almost finished with homework 1B. Again, at the risk, let me just apologize or explain again. Homework 1B is always a big assignment that takes a long time to go through because it frames like a lot of the subtopics for the rest of the semester. It always takes a while to go over. There's always then a backlog of homework 2 and 3 for a little while. And it always comes down to this. So like you're not behind and we're not behind. Like I know it's frustrating probably that we're still on homework 1B. We're just about done with homework 1B, and then things move along faster after that. To be clear, question 9 of homework 1B, like the very last question, is like the point of everything. And I know you've already been exposed to the implications and the solutions in lab. Like that's how it goes. Just like the physicist who came up with all this stuff first saw it in the physical world and then had to work out the mathematics to explain it. So I know, I mean, that's why like homework 2 and homework 3 like got assigned. But I know, but just to be clear, homework 2 and homework 3 are like, homework 2 in particular is like a lot. It's like very long. It's very, very based on the conclusion that we find at the end of question 9 of homework 1B. So if you're still struggling with it, or if it still looks like a big mess to you, or you don't know what's going on in lab, hope is not lost. It always goes in this order. But by the time we land and we walk through question 9 of homework 1B, which would be tomorrow, then a lot of things will fall into play. Hopefully a lot of things you're seeing in lab and the things that were asked in homework 2, like hopefully then they'll all sort of fall into place. It's like, backward classroom. Like you think about stuff and then it gets clarified rather than the other way around, for good or for bad. But just so you know, you're not crazy and I'm not crazy. Well, I am crazy. So why am I saying all of that? Because what we have to finish now is the explanation that we started last class. Like I'm going back to the same PDF of notes. All of these notes were actually uploaded already. So technically you already have these notes, but that's fine. I'm going to go to page 17 of these notes where we were last time. Like also because it's like been a few days, obviously. Like we were right here, I believe. Again, you can correct me if I'm wrong, but I believe we got this far 2 days ago or last time we had class. And so I want to finish this whole explanation. My ultimate goal, the goal of all this is a full expansion on question 4 and 5. You already have the answers to question 4 and 5 of homework 1B. You already have the answers, but this is the full on, like the mathematical, the calculus understanding or explanation of where we got those statements and that method and those answers to question 4 and 5. So more, and again, we're doing all this because we need all these integrals and this integral practice and these closed paths. If you want to know, like, this is all like a big foreshadow to concepts that we really need when we get into circuits, which sounds completely unrelated, right? But a circuit, an electrical circuit, which is ultimately where we're going with this, is a closed path, right? So this is like all laying mathematical groundwork and stuff that we need for later in the course. So what we were saying in the last class, I'm just looking at the chat. What we were saying in the last class, what was this page here? We were saying that the definition of potential energy, like we've always sort of roughly maybe thought of it in our minds, like potential energy is stored energy, right? But what does that mean? And what does it mean mathematically? What we're saying now is it means the energy energy always comes from doing work, right? Energy always gets transferred by doing work. So when you work against a conservative force in order to bring a system away from equilibrium, right? If you work against a conservative force to bring a system away from equilibrium, you do work, you do work, you do work, you give energy, you give energy, you give energy, but then you stop the system. So for example, like if you're working against a spring to bring a mass out to some displacement from equilibrium, like away from equilibrium, right? You do all this work, you do all this work, you're giving the mass energy, you're giving the mass energy, and then you stop and you hold the mass at, for example, 15 centimeters from the equilibrium position, right? Now the mass is stopped, so it has no kinetic energy, but you did all this work. You gave it all this energy. Now it doesn't seem to have that energy anymore. But see, if it was a conservative force, the whole key to all of this is, by definition of a conservative force, we know that the total work done by a conservative force over a closed path is necessarily zero. Like that is what it means to be a conservative force. So if you bring this mass out to 15 centimeters, you do all this work on it, you give it all this energy. Now when it's stopped, even though it seems to have no energy, what we know is because the spring force is a conservative force, we know that if we ever let the spring bring the mass back to equilibrium, we know the spring is going to do exactly the same amount of work back, like positively, as we did negatively to bring it out. Like we know that about conservative forces. So it allows us to predict when the mass is just sitting there. We already know in advance how much work the spring force will do to bring the mass back to equilibrium. And therefore, we already know in advance how much kinetic energy the mass will gain by the moment it gets to equilibrium. So what we say, in order to save ourselves hassle and computational steps, like really, in order to make our lives convenient, we deploy this prediction in advance. We say, oh, we know how much work we did to bring the mass out here. We know the exact same amount of work is going to be done on the mass to bring it back there. So why don't we just say that while the mass is sitting here, it's storing that energy? Like really, we're just saying this. It's like really just in our minds, but it's like but it's not wrong. It's super, super helpful to say when we're dealing with only conservative forces doing work, it's super convenient and helpful to say, aha, if a system is displaced from equilibrium, then we say it's storing energy in the form of potential, and the amount of potential that it's storing, it's not like it's not one formula for all time. The amount of, and so here I'm looking at the page now, like the amount of potential energy that you gain to go from equilibrium out to some other place besides equilibrium, the amount of potential energy you gain and then store when you're sitting away from equilibrium is precisely like this definition right on the page. It's precisely the amount of work that the conservative force would do to bring you back from wherever you're sitting to equilibrium. So it's the integral from x equals x naught, like some arbitrary non-equilibrium spot, the integral from there to x equals 0, like to the equilibrium spot of the path integral of the conservative force, of the force vector dotted with the displacement vector. That's the definition of work, right? So the work that the conservative, so always, so now this is like a memorize. I mean, this is a GDP, a step 3, a definition. From now on, whenever you want to know the potential energy that some system stores, it differs from one conservative force to the next. Like you always have to like recalculate it for every new conservative force you investigate. But once you know what the conservative force is, like in this case of spring, then the potential energy is the amount of work, is defined to be the amount of work that the conservative force would do to restore the system to equilibrium. So that's our definition from now on. And again, remember, what is a conservative force? It's a force that would do 0 work over a closed path integral. Last thing, just to remind you again, we use the definition, we use the idea of path integral over here, and specifically here, we used the idea of a closed path integral in order to define a conservative force, right? Right here on this page, whatever, page 13 or something. A conservative force is one that does 0 work over a closed path. Like notice the circle on the integral, right? Now, having established that definition of conservative force, then we're saying, fine, whatever work that a conservative force would do to bring you back to equilibrium, like not over around, like, so if we're basically saying now, any one-way trip you ever make under the presence of a conservative force, we can consider to be the outward bound leg of a full round trip, right? So what I'm trying to say is notice here in this definition on this page, there's no circle on the integral anymore. This is not a closed path integral. This is just a customary definite integral. Okay, so that's like where we picked up, like, I mean, that's where we left off a few days ago. So now I'm saying potential energy is the work done by a conservative force in order to restore a system to equilibrium. Now, sorry. Okay, wait, I'm looking at the direct chat. X supposed to be here. What is that symbol right before the X? Good question. So someone in the direct chat is asking, what is that symbol right before the X supposed to be? So if you, right before that, you mean in the integral? I think, okay, wait, here, let me write this more neatly. I think you're asking this, but I'm not sure. Tell me. And if not, well, I'll make it all neater, then you'll tell me. So this is supposed to be a dx with an arrow over it. This is supposed to be literally a dot, which I'll talk more about in a second. This is supposed to be x equals x naught, and this is supposed to be, sorry, x equals 0. I don't know if this is what you're asking. So this whole thing is supposed to be a definite integral from the position x naught to the position to the position 0, and technically this is a path integral. In other words, it's an integral of a dot particle. Let me see. Oh, is that? Where the F? Oh, where the F go? Oh, hang on one second. Hello, welcome back. I'll be doing. Hello. All good? No. Great. All right. I got to teach, but good job. I'm noting it. I understand. Okay. And then you'll tell me the phone. Well, okay. So let me teach you.
Yeah, no one answered my calls.
What you call? Did you?
Yeah, I called you and I
okay, but I did. All right, but I did say I was teaching. Okay, I got to teach now, but then we will all.
Okay.
Okay, love you.
Can I have when you're done teaching?
No, Felix, stop.
Fine.
Okay, sorry. I need to teach. That's funny. Oh, they all say hi. They say hi, and they say they need you to teach. Okay, he says hi. Okay, thank you. But wait, did I get the symbol correct? Wait, it looks like I did where it goes F equals. I'm just making sure because again, I always love these questions because I'm sure the person who's asking is like not the only one who. Wait, where? Well, okay, where it goes F equals. Okay. Well, as long as I got it. Okay. Wait, but let my, right, I know. And that's rough because he's off from school and let him cook. No, what he wants is, okay. No, it's a little tricky because he's off from school and we're here, so it's all a little bit, and he knows he's, anyway, okay, wait, never answered the phone. Oh my God, Michelle, all right. And I answered the phone right before, anyway, okay. Okay, so that's that, but feel free to, okay, I'm gonna, oh, dude, it started a long time ago. Are you kidding me? It started, I mean, at least it started last semester, but way before that. Okay. The alpha villain, no less. Okay. Okay. So in sum, then potential energy is the ability to do work by virtue of an unstable configuration. What do I mean by that? Okay, again, I'm just trying to, by the way, again, remember, I know it's confusing or possibly, this is all in the context of question 4 and 5. Like we answered them, we got answers, but we use this thing called total mechanical energy conservation. And right now I'm trying to back up and actually both justify and hopefully teach or explain what this total mechanical energy thing really is all about. So remember kinetic, so all energy, what energy is the ability to do work. But there's different, right? And work means pushing or pulling something and moving it through space. Like literally to do work is to interact with another object and change its position. That is literally what it means to do work. Why? Energy is the ability, the capacity to do that. The most obvious reason you'd have the ability to do that is kinetic energy is if you're already moving. If you're already moving, you can slam into something else and move it. Like literally, it's that like dumb. I mean, it's not dumb, but it's that simple. Kinetic energy is the ability to do work by virtue of motion. You're already moving, you can move something else. But now what we're saying is, okay, potential energy then, just to summarize in English, potential energy is the ability to do work by virtue of configuration, which is a fancy way of saying the way things are arranged, like where you are. It's not, so you might not already be moving, but if you're in an unstable place, if you're in a position that is not equilibrium, then we can predict in advance what will happen to you if you start moving back toward equilibrium. The reason you would move back to equilibrium is a conservative force would start doing work on you to bring you there. So you would eventually speed up and get kinetic energy. So we can already predict in advance. Okay, so potential energy is the ability to do work by virtue of an unstable configuration. Again, that only would ever come up. It only applies if the forces doing work, if the relevant forces doing work on the system are conservative. It's completely not a thing if all we're talking about is like friction or tension or normal. It's all right. Anyway, so that's the summary of that. Therefore, now that we've established this idea of potential energy and kinetic energy, now we could say, fine, because we've almost made up this idea. I mean, we didn't make, but because we have this shortcut called potential energy now, which really is just a prediction of how much kinetic energy you'll end up getting, we can say at any given place, whatever kinetic energy, any given place you are under the presence of conservative forces, any given place you are, whatever you're lacking in kinetic energy, you're storing as potential energy and vice versa. So the sum total that you have at any given place is a constant, just because of the way we just defined potential energy. Potential energy is the amount of kinetic energy that you're missing right now, but we know you're going to get back. So at any given place, if you add those two quantities together, you should always get the same number, right? So that's why from now on, we define mechanical energy, capital E sub X, we define it to be the sum of kinetic and potential. Like there could be a lot of different forms of potential. You could have potential due to gravity plus potential due to a spring, like technically in lab 1, that was what was going on. But there's only, so you can have a lot of different kinds of potential energy. You can only have one kind of kinetic energy, and you add those things together, you have the sum total of your total mechanical energy. And notice the subscripts, I am about to go on, but notice we define E sub X equals KE plus PE sub X, meaning it's defined with respect to a particular position in space. That's the whole idea of it, is it's a number that doesn't change from position in space to position in space. Okay, so therefore, E at one position in space equals E at another. And generally the one position you're picking is a position that you're solving for, and the other position is a position that you know everything about. So ultimately, the purpose of this, as we said 2 weeks ago, the purpose of this idea of energy, of mechanical energy conservation is, and for those of you who are like, had been turning in notes for points, which I'm very grateful. If you're turning in notes and like showing that you're writing down things that I don't necessarily write down, here's a thing to write down, is that we use mechanical energy conservation whenever we're interested in a speed to spot correspondence. That's what it's all about. Speed to spot, like speed to position correspondence. If you know the speed at this position over here and you want to know the speed at this position over there, that's when you use this, or vice versa. You know the speed at this position over here and you want to know the position at which some speed occurs, which is like a question 5, that's when you use this. Okay, but it's only true if all of the forces doing work on the system are conservative. Okay, which is the case in this homework, because the only force doing work is a spring force, and a spring force is conservative. Okay, now that we've said all this English, I want to do some math. Like my goal now, in order to have established what's happening in question 4 and 5, like the real issue is, how does all this abstract English discussion of potential energy apply to a spring? Like literally what I have to do now is use this definition, this integral, to actually calculate what is the potential energy function for a spring. Like I'm going to calculate it once and then it'll be true for all time. It won't be the same function as for gravity. It won't be the same function as for electricity, but it will be a function that will for all time apply to springs. So that's my goal, is now to calculate the potential energy. Yeah, my goal is to compute the potential energy function for a spring. Like, for example, what you might remember or know, or you can revisit, is like for gravity near the surface of the Earth, I should say, the potential energy function happens to be mgh. Near Earth's surface, the gravitational potential energy happens to be mgh. Now, you might have already memorized that. You might have seen that. Where did that come from? Strictly speaking, that was the work that gravity would do on a mass to return it to a height of 0 from a height of h. Like that's what that is. Strictly speaking, that is the integral of the force mg. Like strictly speaking, that is the integral from h to 0 of the force of gravity dot dx, or dy if you want to call it, right? Strictly speaking, that's an integral. But it's not really a hard integral. Like I'm not going to redo it right now, because the force in that integral is mg, and mg is a constant. It doesn't change from position to position. So it comes out of the integral. So you end up having mg times the integral of dy from 0 to h. So that's just, I know I'm saying this fast, but for those of you who are getting more and more comfortable with calculus, like I should almost ask this in the chat. If you want, like, I'm going to keep talking, but feel free if you want to like grab some major points and major karma, feel free to put in the chat if you want, if you're hearing me, like the integral, the definite integral from y equals 0 to y equals h, the definite integral from y equals 0 to y equals h of y. Sorry, I'll say it one more time. What is the definite integral from y equals 0 to y equals h of dy? Like literally, the integral of dy. In other words, what's the integral of dy? So it's not a trick question, but it might be tricky to do in your head. But what's the integral of dy? Just dy. The integral of dy, if evaluated from y equals 0 to y equals h. Like, what is that integral? And I'm looking. Oh, can I repeat? Oh, sorry. Oh, sorry. I'm looking in the chat. Okay, I'll back up for a second. I see things are happening in the chat. But yes. Oh, wow. God, you guys are awesome. Like, I kind of like, lost the chat after origin story, but yeah. Wait. So, I mean, Maria is right. The word, where did I write it? Yeah. Whenever I wrote, like, as long as all the forces doing work are cons, yes, I did mean conservative. Thank you, Maria. And thank you, Fariel, for asking, but yes, cons equals conservative. Thank you, Katie. Yes. Now, can I repeat that again? So, and if there's more questions on that, if you want me to turn back the page, I'm happy to. What I'm asking now, this is just like sort of for fun or to keep us paying it, not fun, but what I'm asking is, I'm not quizzing you. I'm just saying if you want to put an answer in the chat, and it's not a race, you could put it in direct chat. Okay. And you remember, you'll get credit for doing it, whether you get it right or wrong. I mean, you'll get points. But what I'm asking is, what's the integral of dy? Like literally, what's the integral of dy? But let's say the definite integral of dy. So from y equals 0 to y equals h. Like, what would you literally get? It's not meant to be a trick, but so what's the integral of dy? Like, do that and then evaluate from 0 to h. And I'll wait till the second. I am going to wait until I get like I'll say 2 answers in direct chat or public chat. I'll say it again. What's the integral of dy? Like, really, that is my question. What's the integral of dy? But to get a specific answer, what's the definite integral of dy from y equals 0 to y equals h? I'll wait for a second. Good. I see one thing in the direct chat that's really close. That I see what the person's saying in the direct chat. It's a really good idea. It's not quite right, but good. But that person should definitely. There's only one person in the direct chat. So if you're in the direct right now, so if you're in the direct chat, you should definitely submit for points. And I'm admitting that your answer is not right, but that means you can also submit in the portal that says be wrong, be really wrong. It's not like an insult. You literally can get extra points for the fact that you were like had the guts to do something wrong and handle it okay. So direct chat person, I hope that's clear. But now I see something in the Christopher Ram chat. I mean, in the everyone chat. He's close. He's getting there. Okay, yeah. And then I see something else in the direct chat now where someone's saying, would it just be finding the indefinite integral and then find the actual value with the limits? So yes, I agree. So the limits are from y equals 0 to y equal h. So there literally is an answer to this. It's not a numerical answer, but there is an answer to what I'm asking that involves like the letter h. On the right track, I'm seeing things in direct. Okay, so a lot of people in the direct chat now. Every one of you that's putting in the direct chat, you really should submit for points. And I am proud of you for playing with me, like seriously. And it happens that a lot of the things in the direct chat are wrong. But what that just means is that this is worth me stopping and discussing. It just means we're getting our money's worth. Okay, honestly. Okay, and now I see more. So I'm going to stop. I like these answers and I appreciate the guts. I should also open a portal for like, it's even more gutsy to go public, obviously. And I appreciate that. I'm going to say this. Hold on. So I'll even write it down just as just so we can be clear. Hold on. Let me just add a page. This is what I'm asking. So most of the answers are not totally right. There's one answer that's close to right. So bear with me a second. This is what I'm asking. I'm asking this. It's a sidebar, but I'll show you why I'm asking it in a moment. Like this is what I'm asking, right? And the person who's got the answer closest, or in fact, everything he or she is saying is right. It's just, it's not totally complete. Someone is saying in the direct chat, would it just be finding the indefinite integral first? And then that person says, which is y, and then find the actual value with the limits. Well, that person is correct. Like the integral of dy by definition is y. The integral of dy is y. And you do want to know that. I mean, like from here on in, that is, you could even memorize that if you want, or you can do the power rule in reverse if you like. But that's really the definition of an integral. The integral of dy means add up a bunch of infinitesimal portions of y. It means walk along the y-axis, adding up all of the infinitesimal segments of the y-axis as you go. That's what that. So the answer is the total y. the sum of all the infinitesimal fractions of y is the whole y. Like that really is the meaning of integral. And if we're doing a definite integral, we mean start at the value y equals 0, walk all the way to the value y equals h. So like the person in chat is saying, like you do the integral first and you get y, and then you evaluate from y equals h to y equals 0, right? So that means plug in h for y and it means like this. So what you get is h, right? Now, why? Yeah, antiderivative. Yeah, or yes, what Chris is saying. Now, why did I just ask that? It sounds like I'm like totally off the topic, but what I'm showing you is this. And I'll put these pages back in the right order in a second. I'm saying then the potential energy due to gravity. If you want to know the potential energy due to gravity, you want to know the force. I mean, you want to know the work that the force of gravity would do to bring an object down from a height or you want to know how much work the force of gravity would do from the height of h to bring it down to the height of 0. All right, I'll be technical about it. You want to know, if you want to know the potential energy due to gravity, you want to know the work that gravity would do to restore some mass m from a height of h back to the equilibrium height of 0. Like by definition, that's what it means to calculate the potential energy due to gravity. So if the force is mg negative, like pulling down, right? And you're integrating that from the top to the ground, right? I'm showing you how we apply the definition of potential energy to get potential energy for various functions. What I'm showing you right now is how we get the potential energy due to gravity that you may have seen, that you use for the rest of your life. And I'm starting with this one, first of all, because it's more commonly known, but also because it's one step less complicated than the spring one that we really need to know. So I'm like, okay, so we're just like practicing first on gravity. You would plug in the force of gravity, negative mg, and then you would say, negative mg is a constant. What do I mean by it's a constant? I mean, it doesn't depend on y. It doesn't matter whether you're here or there or there. The force of gravity is still the same. So the negative mg comes out of the integral. Well, here, even more technically, let's say. The mg comes out of the integral. Then I'll leave the negative sign in there for a second to show you something. And then because there's a negative in there, and that's annoying, what you know from calculus is I can get rid of that negative by flipping the limits of integration, right? Because ultimately I'm going to subtract. So if I do the subtraction in the opposite order, it's just like multiplying by -1. So it becomes mg without the negative sign from y equals 0 to y equals h of dy, right? And stop me if this is not making sense. But I'm saying if we were calculating the potential energy due to gravity, this is what we would do. And the mg would come out of the integral because it's constant. So we're just left with the integral of dy evaluated from 0 to h, which is the question I just asked you in the chat, and you all very nicely like participated in. So we would get, so that's why I just asked, what's the integral of dy? Because the whole integral just reduces, once you take the constant out, it reduces to this comparatively straightforward integral. So you get mgy evaluated from y equals 0 to y equals h. So you get mgh, and that is the potential energy due to gravity, right? That's just a practice exercise there. That's how so from now on, as long as you're near the surface of the earth, the potential energy due to gravity is mgh. Really, if you step all the way back and look at it, what we're really saying is force times distance. The force of gravity is mg, the distance is h, boom. That's what we're saying. right? It's that straightforward because the force doesn't change along the path of distance. Now, I'm just looking at the time. Okay, so first of all, let me just put those pages back in the right order. That was like a sidebar, but it goes. Pardon me for a second. It goes. Yeah. All right. So here's that's. And okay, so that's the sidebar we just did. So now, right? Okay, so gravity is MGH, like we were just saying. Now we can go back to where we were, which is, can we take this same concept? Oh, thank you. Okay, thank you. I think the whole word "cook" is okay. Thank you. I think so. Now, if that's gravity, now we're going to apply the same concept. I almost should ask you in the chat, but maybe I won't. We're going to do the same concept now, but for the work done by a spring to restore a mass to equilibrium from not from a height h, springs don't care about, but from an arbitrary displacement known as x naught, like a horizontal displacement on a horizontal spring. So what do? We do the exact same concept. We say that we have to calculate the work done by the spring to get it from x equals x naught to x equals 0, right? So the work is the force of the spring, is the path integral of force times dx. Now, I'm going to pause for a second. Am I? Well, I'm just going to make a technical point that I will expand on more later. But remember, when we first learned about work, like last semester, work is strictly, it's not just an integral, it's a path integral. That is to say, it's an integral. Now, everything I'm about to say, I could have just said in the last example with gravity, but that was meant to be an easier example, so I just didn't get bogged down. But everything I'm about to say like applies to all of these concepts of work and energy and so forth. And that is that work, it's not just an integral. It's strictly speaking, it's the path integral of force. That means it's the integral of the dot product of force with respect to displacement. It means we're taking the force vector and dotting it with the displacement vector. Wait, did you do this in the lab? Wait, I'm looking. Wait, I can't actually in the lab. I'm not sure what okay, you can expand on that. I feel like that's a relevant point. But okay. Oh, in the lab, I think I get it. Okay. Dot product is a way of multiplying two vectors. It's not the only way. We're going to see another way soon, but it is a way of multiplying two vectors. The dot product is the way of, in fact, I'm going to insert another page here just to make this as clear as I can, because we do have time. Okay, to make this as clear as I can. I know it says it on the other page. I'm just trying to make this more explicit. Okay. If you're given any two vectors, now this comes back, we did talk about this in other terms last semester, but I'm just saying it more with more mathematical explicitness now. If you have any two arbitrary vectors, like two different magnitudes, two different directions, say vector A and vector B. So they're pointing in two different, so they have two different lengths, right? They're two different arrows, but also if they're pointing in two different directions, you could picture an acute angle theta that is the separation between those two vectors, like the difference in their directions, call theta, right? The dot product of those two vectors is defined to be the magnitude of one vector times the magnitude of the other times the cosine of the angle between them. Right? Like when I write A and B without arrowheads above them, I'm saying just the lengths of those two vectors. So I'm saying, notice the left side, it involves vectors. It's a form of multiplying two vectors. But the right side doesn't have any vector symbols in it. It doesn't have any arrows. The right side, and that's not a typo. The right side is a pure number, whereas no direction. Whereas the left side is two quantities that have direction being multiplied by each other. So the whole idea of this operation is when you dot two vectors together, you're calculating a product of those two vectors that does not have direction in the final answer. You're getting a scalar product of two vector quantities. And the way we're doing it is, in effect, we're measuring the extent to which the two vectors are parallel with each other. Like we're saying the closer they are in direction, the less they differ by direction, the less of a role direction is playing in their relationship, then the bigger answer we get at the end. In other words, take it to an extreme, the cosine, and you do want to know this, like I should almost ask in the chat, but I don't want to get too rabbit holing it. Remember, the sine of 0 is 0. The cosine of 0 is 1, right? So cosine is the one that the cosine of 0, when two arrows are parallel with each other, they have no angle between them, they're perfectly aligned, their cosine is 100%. As the angle gets bigger and bigger, as the two vectors get more and more perpendicular to each other, as their directions start differing more and more, the cosine goes down all the way to the point where if two vectors are perfectly perpendicular, if they're fully differing in direct, like they're on two different axes, then the cosine is 0. So the dot product of two parallel vectors is as big as it can be. It's the length of one times the length of the other. Because if two vectors are parallel, they're both lying on the same axis. Then we're just like multiplying two numbers on a number line. Their directions playing no role at all. But as they get farther and farther apart, we take their lengths and we multiply by a smaller and smaller fraction called the cosine of the angle, until the point where if they're so far apart that they're at right angles, then we get no dot product at all. So the dot product looks at the extent to which two vectors are lined up. We use the dot product to calculate work because, like we said last semester, when a force is displacing a mass, we only care about the component of the force that is lined up with the displacement, right? If I push a box at an angle across a floor, some of my push, if I'm pushing at an angle, some of my push is going directly into the horizontal displacement of that floor. That component of my push is doing work. It's transferring energy to the box. But whatever amount that I'm pushing down or up, that's not helping the displacement at all. So that doesn't count. So when you're calculating work, you multiply the length of one vector times the length of the cosine component of the other vector. You're multiplying the components of the two vectors that are lined up with each other. That's what the dot product means. That's what we're always strictly doing whenever we calculate work. Whenever we do a path integral, we're strictly doing an integral of a dot product. Sometimes it makes a huge difference. Sometimes it doesn't. I'm just reminding because we need that to know that. And we're going to contrast it with a different form of multiplication, vector called the cross product a little bit later. So, and this, as you might have noticed, it comes up in in homework 2. So I'm just trying to explain a little bit more now. So that's what the dot product is. Okay. That was another sort of math sidebar. I'm just going to put the page back in place. So that's what the dot product is. So back to this page, then, if we're going to calculate the work done by a spring force as it brings a mass in from x equals x naught to x equals 0, strictly speaking, we're doing the dot product of the spring force, negative kx, times the displacement dx, times the cosine of the angle between them. We're sort of practicing. I'm just getting used to how this math works. whenever, so if you want to get rid of the vector symbols and like just turn this into, like it all looks intimidating at first, but if you want to turn it into an integral that you actually can do, if you want to get rid of the vector symbols, you write out the definition. The dot product of f with f vector with dx vector is negative kx times dx times the cosine of the angle between them. But now, having said all of that, having just taught you all that, the truth is the angle between the spring force and the displacement, if the spring is pulling a mass just purely horizontally, the spring force is horizontal, fully horizontal. The displacement is fully horizontal, so the angle between them is 0, so the cosine is 1. So even though I just said all of that to be strict and rigorous and mathematical and correct, it doesn't end up amounting to any issue here. The cosine goes to 1. So if the integral of negative kx dx, right? Okay, that's what I was. So again, I'm trying to calculate the work done by the spring as it brings a mass back to equilibrium. So far, I have the integral of negative kx dx. So I go to the next page. So I have the integral, there, just repeated at the top, the integral from x equals x naught to x equals of negative kx dx, right? So first of all, just like before, like with the gravity thing, k, the spring stiffness constant, is a constant. It might change from spring to spring, but it doesn't change within one example that you're looking at of one spring. So K comes out of the integral, right? Like in this case of homework 1, I mean, it's like 200 newtons per meter. It's a number that doesn't change. So K comes out of the integral. So now we have the integral of negative x dx. Just like we did in the other example, in order to get rid of that negative sign, I'm going to flip the limits of integration. So I have x equals 0 to x equals x naught. So now I have the integral of K. Now I have the work that I'm trying to calculate equals K times the integral from 0 to x naught of x dx. Now, this is an actual integral, right? I'm not saying it's super hard. If you've ever done any integrals, this one is not so bad. I mean, you don't have to use a U substitution or integrate by parts or any of that kind of stuff. But you do, and this is kind of like what Chris said before. For this one, like you do have to do like an antiderivative. You have to get the integral of x dx. Like it's not a joke. It's not a memorizer. How you have to do the power rule for derivatives in reverse, right? Backwards. It's an antiderivative. So with derivatives, and stop me if you don't know what I'm talking about here, or text me or email me or whatever. But remember, I should almost, I'm looking at the time. Wow. If you had, the derivative of x squared, you would lower the power by 1. Sorry, you would multiply the whole thing by the power and then lower the power by 1, right? Like the derivative of x squared is 2x to the first, right? Well, we're doing that backwards here. Instead of multiplying by the power and then lowering the power by 1, we're literally doing that in reverse. So we're raising the power by 1 and dividing by that new power. So again, I should have asked this in the chat, but the integral of x dx is x squared over 2, right? And the k has already been taken out of the integral. So this integral is kx squared over 2, but then evaluated from x equals 0 to x naught. So we get that the work that so this is like, do you see? It's exactly like the gravity thing, but it's one step more complicated because we actually do have a variable in that integral. It's not all constants. It's x dx rather than just dy. But so we get that the work that a spring force would do to bring a mass in from equilibrium would be 1/2, to bring a mass in from the spot x naught into equilibrium would be 1/2 k x squared. It would be 1/2 k x naught squared. That's what we just calculated was the work that would be done on the mass to bring it in to equilibrium. But therefore, the whole purpose of all of this is that is the energy that a spring stores in the form of potential. So from now on, just like we can say gravitational potential energy is mgh, we can from now on say spring potential energy is 1F kx squared. So that's where we got this idea, back to question 4 and 5, that at any given spot, the total amount of energy, the 1F mv squared plus the 1F kx squared over here, is equal to the total 1F mv squared plus 1F kx squared over there. Like that's where that came from. So from now on, we know spring potential energy is 1F kx squared. It came from the definition of potential energy, which is work done by a conservative force to restore a system to equilibrium. Okay, so that in my mind, what we just did, maybe somewhat confusingly, what we just did is we just expanded and explained the concepts underlying question 4 and 5. The concepts were conservative force, closed path integral, potential energy, and finally, total mechanical energy conservation. So now the answers to question 4 and 5 were V equals 3.87 meters per second and X equals 0.095 meters, but I think you have those answers already in your notes. So I'm considering now question 4 and 5 to be done. And I want to move on. The big goal is to get to question 9. We're going to start and finish question 9 tomorrow. But right now, with like the 23 minutes left, I want to kind of zip through, or maybe we'll even start question 9 today, but I want to zip through, I want to stay in order. So I'll quickly zip through questions 6, 7, and 8 of homework 1B. But all right, I'm gonna take a breath here, but definitely. So we're transitioning now. I think we're done with everything that you need for the rest of the course in terms of potential energy, conservative force, all that integral practice. I mean, you're not done with integral practice, but like we're done with that. So now moving on to, so I think we're done with question 4 and 5. I'm moving on to question 6, work 1B. So that's a good place to pause for a second and like look over your notes for a second and see if you have if you make sure you know where I am like in the material. And again, you're way ahead of me. You've already turned in homework 2 and homework 3. That's great. You still can get more feedback or more point. You could still revise, upload, change more. Like you're not late. And we're not late. Like we're fine. But so take a moment to make sure you get what's going on so far from the lecture material. I'm just looking in the chat. Oh, there is. Oh, sorry, there is stuff in the chat. Sorry, that was stuck. Hold on a second. Oh my God, it was like a long time ago. I'm sorry. I'm gonna look in the chat right now. Hold on. Okay. There's a trig function of cosine. Oh, really great question. Okay, I mean, there's more than one. Oh, no. Well, all right, there's a really good question here, and then the person tells me to disregard the question because like they figured something out on their own, and that's great, but I still like the question though. So I'm just gonna say, but with double respect to this person, like both for asking it and for like working it through in their mind. The question says, does the trig function of cosine change to sine if the location of theta changes, or will it always be cosine when talking about dot products? No, that really is a good question. So the simple answer is when we're talking about dot products, it is always cosine as long as it's always cosine of the angle, as long as the angle, we mean literally the acute angle between the tails of the two vectors. So this is why this actually is a good question. I'll try not to get bogged down in it. But like you could have a picture of like someone pushing a box along a floor, and the way that someone might draw the picture, like they might be highlighting in their picture an angle that's like different from what I'm picturing right here. And so then if the angle that they're highlighting in their picture might be like something else for other purposes, then there you might have to like redo an angle or do a sine instead of a cosine or something. But I'm saying once you lift the vectors out of the picture in your mind, once you look at the two, like if there's a force vector and there's a displacement vector, if you move the vectors on the page and you put the two vectors tail to tail and look at the acute, like the smallest possible comparison between the two vectors, once you make your own diagram and put the force vector and the displacement vector tail to tail, then yes, you take the cosine of the angle between them in order to do a dot product, in order to do a dot product, in order to do a scalar product between two vectors, in order to get a non-vector answer to the multiplication of two vectors, you always take the cosine of the angle between the two vectors. And yes, furthermore, the dot product is always the operation that we choose when we're looking at work done. Like it's the dot of force vector with displacement vector. Now, the person who's asking this it really is a good question, because it is true, just to be clear, that pretty soon in this class, we're going to have this other operation called a cross product, where you multiply two vectors. In fact, it's in the end of homework too. And it gives you the definition, and it doesn't explain things. I mean, it's like hard, but it gives you all the information you need to try it in practice. And I'll explain more like soon, but it turns out that the cross product between two vectors is the product of two vectors that yields a vector. So the cross product looks at direction and cares about direction and looks at how much the directions of two vectors differ. So with the cross product, once you draw the two vectors tail to tail, then with the cross product, we always use sine. I'm just like, that's whatever, whether that's to help you with homework too, or foreshadow, or spoiler alert, or to answer that question. So yes, but the dot, as long as you draw your vectors tail to tail, dot product always takes a cosine because it's always looking at how parallel they are, and the cross product always takes a sine because it's looking at how perpendicular they are. So great question. So that's that. So great question either way. And then, okay, Calc 2 is a living nightmare, traumatizing. Okay, again, back to that. Fair enough. Like, I'm with you guys. It almost traumatized me, but we're here for group therapy. Like, I didn't like calculus when I first took it either. I didn't get it like the first 4 times I took, or whatever. But don't give up on yourself or the material. It is more interesting than it seems at first. And we're more to the point. I don't even care if you, well, I do care if you find it interesting. But even if you don't find it interesting, it's more doable than it looks at first. I promise. But you just need to see it alive in physics. Well, some of us need to see it alive in physics, and we need to go through it over and over again. It's just that way. But anyway, but yes, I see you and your trauma. The insanity in me sees the insanity in you. I promise, like namaste, whatever. Okay. Or insanity. Okay, so now we got 16 minutes. I'm going to do question 6, 7, and 8, but as it says right here, I'm not going to do a 5-step method on them. First of all, it's hard to, they're sort of quick and dirty questions. Anyway, I don't really expect you to have done a 5-step method on these questions in the homework, but I do expect you to explain your answers, which I'm going to try to do right now, but just to save time, I'm going to be sort of quick. So question 6, and we already have the diagram from above. Question 6, question 6 was, where is another X such that V equals 0, right? In other words, ask, when's the next time the mass comes to a stop and then thereby turns around? Well, I'm sure many of you would, many of you, I think, just saw an intuition in your mind or guessed, and correctly guessed, that the answer we're looking for here is X equals negative 0.15 meters, right? In other words, exactly as far on the other side. If you just figured in your mind, well, I guess this thing is symmetric, you're right. But what's the explanation? Like, why are you right? The reason you're right, that the next time the thing will stop is exactly as far on the other side, if you really think about it, is because energy is conserved. Like, now that we're saying this, if you know that x equals 0.15, v equals 0, and you're looking for the other time when v equals 0, the only other time, then you're solving for x squared on the other side. And there's two roots to x squared, positive 0.15 and negative 0.15, right? That's the only two possibilities, the only two numbers that could both generate the same solution of v equals 0 must be the additive inverses of each other. I mean, I'm saying that like badly, but I'm saying the reason this thing must be symmetric. What I'm saying is this: energy conservation means symmetry in time, right? If you're just assuming, I bet it's symmetric, you're right, but that's because this thing conserves energy. Put it on one last final way. If there were friction doing work on this thing, then that answer wouldn't be true. But we've been assuming there's no friction the whole time. So anyway, I'm sure most of you got this right and good, fine. So that's number 6. We're just trying to reinforce. So why we're going through these questions is we're trying to say now, from now on, this type of oscillation, this type of back and forth behavior, from now on, we'll always conserve energy and we'll do all the things that anything that conserves energy does. And so from now on, any system, we're painstakingly obsessing over a mass on a spring, because we're going to say, for as you've already seen in lab number 2, like we're saying that from now on, there's a lot of systems in nature and in life that all resemble masses on springs. And if they resemble a mass on a spring, then we're saying from here on in, all the physics and all the math that we believe for a mass on a spring will apply to all of these similar systems, all of which we're going to call oscillators, right? So so from now on, energy conservation is true, and it implies symmetry in time. Therefore, question 7, yeah. When it asks how many like trips or round trips or whatever will occur before coming to rest. Well, if everything we're saying so far is true, if we really believe energy conservation, and if we really believe that if it starts at 0.15, it's going to get to the other side negative 0.15, then when it gets to negative 0.15, it has the exact same amount of energy that it had when it started at 0.15. So it should be able to travel the same distance again. If it's really conserving energy, it's going to keep doing this forever, right? Now, pause for a second. Like, that's quite a claim, forever. Like, obviously, it doesn't do that in your lab, because your lab is not really optimal conditions. But 2 quick things to say about this. I don't want you to think this is a lie. Or I don't want you to think, oh, yeah, like in like physics fiction land, this is true, but like this has nothing to do with the real world. It has a lot to do with the real world. 2 quick points. Number 1, I don't want to dwell on this, but when we say it's going to take infinite number of trips, first of all, if you suddenly think like, wait, this is BS, I understand why you think that or why you would say that, but let's get it straight. The BS part of it, like the lie or the super duper optimization, idealization, and approximation, is that energy is being conserved. When I write the infinity symbol now, you might think that's ridiculous, but please note, it's no more ridiculous than the answer we got for question 4 when we said the speed at the center was 3.87 meters per second. I just want to be clear about this. 3.87 meters per second that we got in question 4, and then 0.095 that we got in question 5, those assumed perfect energy conservation. They look like regular everyday numbers, so they seem acceptable when we get them. You're like, oh yeah, that seems reasonable. Okay, 3.875. Suddenly this looks like a big lie. But I just want to be clear, this is no more of a lie than 3.87 or 0.09. Don't be fooled by precise numbers into thinking that just because they have precision, they have accuracy, right? So number one, to whatever extent this is an exaggeration, the whole sheet is an exaggeration. Okay, that's number one. But number two, that's all it is an exaggeration. I'm just going to say this quick. I'm going to say this a lot during the course. I'm going to try not to get bogged down. I know we have 9 minutes, but remember whenever we say things like negligible friction, right? Okay, we assume a system that has negligible friction, right? And most people when they hear that in physics, they tend to just be like, yeah, physics. Okay, negligible friction. So we're just talking about Smurf Village. We're talking about like unicorns and rainbows and negligible friction. Okay, whatever, teach. Like what people tend to do, or certainly what I tended to do. Whenever I heard negligible friction, I'd be like, all right, I'm going to accept that assumption. I'm going to write down the equations. I'm going to, do whatever you're telling me, teacher, professor, and I'm going to get the answers. But like deep in my heart, I'm going to know this is all crap. Like if you're talking about neglecting friction, like you're not talking about the real world. We're just being like mathy here. I thought we're not being sciencey, and that's right. So I would just get through and do that. But of course, more and more I did that, the less and less I thought of it as science, the less and less I thought of it as real world. And I just thought of it as like crap to memorize, which meant once the pile of memorizing things got big enough, it got really hard to manage, right? And once they started telling me, no, this makes sense. This is about the world. It was like too late to a point for me to like think about it in a sensible real world way. Let me remind you, every time we say neglect friction or friction's negligible or the displacement of the mass is really small compared to the length of the spring, or like all these like optimizations and idealizations we're not making them because we're just being mathematical. Actually, we're making them because we're being scientific. Just please remember at all times that what makes science science and what makes any of our science stuff believable and true and real is that it all comes from measurements, right? The difference between science and math, and I love them both, but math is like the pure language of theory or whatever. Science is about measurements. We only believe that which we see on a measuring device, right? And if we don't see it on a measuring device, we have no basis for believing it, or if we can't reproduce it on a measuring device, right? So every time we ever say something like in the limit as delta x approaches zero, or in the limit as friction approaches zero, what we really mean is in the limit as the amount of friction falls under the threshold of measurement. And therefore, like we don't believe it anymore. And so if we say friction is negligible, we mean it means we're not like it's City University with like a $2 budget and like 1 hour to do things. It means we're in a fancy lab with really expensive equipment and lots of time and like a government motivation on our end. And we're setting things up so nicely that the friction falls so below the threshold of measurement that the thing doesn't swing perfectly all the way to 0.5 on the other side, but it swings to like 0.149999999. It differs from 0.5 by such a small amount that our measuring equipment can't even pick it up. That's what we're saying. And that's what makes it real and actually real. Every time it looks like we're talking about perfection, we're really talking about imperfections that fall below the threshold of measurement. And that is totally possible, not always in an hour and a half lab at City University, but in the world it is. Just okay, so that's my point. So the answer to this one's infinity, which means effectively infinity, means goes on longer than we can measure. Totally possible. We have 6 more minutes. So that's the answer to 7, which traumatized. Okay, no, that's the old. Okay, then number 8. Now the most interesting, we're going to end with number 8. We'll do number 9 tomorrow. Number 8. Remember, it asks like in the first fourth of a cycle. I'm just redrawing the diagram so you can picture what we're talking about here. Right, we're asking right? Like a cycle would be all the way to the other side and all the way back. So a half a cycle would be all the way to the other side. So a quarter of a cycle would be just to equilibrium, right? This question is talking about in that first fourth of a cycle, just from x equals x naught to x equals 0, we're asking about the magnitude of velocity, like what happens to it, in other words, dx dt. And then we're asking acceleration d2x dt squared. And then we're asking this new concept that we hadn't really thought about last semester, jerk. The guy in the front of the Zoom room with the jacket on. No. The third derivative of position with respect to time. We're asking for each one of these, are they going up or going down or what? Some of them are easier to figure out than others. My hint for doing this, so this is what we're being asked, right? We're being like asked up, down, or remain constant. We have 4 minutes left. My hint for this is, since we're being asked the first derivative, the second derivative, the third derivative, it might be useful or helpful if any pattern is detectable. So even though I'm not asking, I'm going to back up and look first at the function itself, at position. It's not asking that, but I think it would be helpful to me. So in other words, we have 3 minutes left. The position, as it goes from x equals, in other words, x equals 0.15 meters, as it goes, and we're just looking at magnitude. I'm not care about plus or minus signs, just the size. So as it goes, as the mass goes from 0.15 meters to 0, the position is clearly, I mean, it's not a trick. The position is going down. The value, the absolute value of the position from 0.15 to 0 is going down. What's the velocity doing? Well, at x equals 0, we said the velocity was 0. That's a premise of the problem. It starts from rest. And then we know that by the time it gets to x equals 0, it has a high velocity of 3.87 meters per second. So clearly the velocity is going up, or the magnitude of the velocity is going up as it comes in, which means the thing is accelerating, right? It's changing its velocity. It's accelerating on its way in. But now this is slightly tricky, and you might want to think about this. It's not a contradiction, but it is tricky. The thing is getting faster and faster on its way in. It is accelerating. But its acceleration value is not going up, nor is it remaining constant, right? While the thing is gaining speed, it's gaining speed at a lesser and lesser rate. How do I know that? Well, first of all, look at our answers for question 1 and question 2 and question 3. At the edge, at x equals 0.15, it's the force on the mass is huge. F equals ma, it's producing a huge acceleration. We found in question 2 or 3 or something that the acceleration had a huge magnitude of 100 meters per second squared. It was negative, meaning it's pointing in, but I'm not caring about the negative sign. The magnitude of the acceleration was huge, like the magnitude of the force, because it's all the way out here on this really tight spring. As it comes in, by the time it gets into equilibrium, we found that the acceleration, just like the net force on the thing, is 0, right? It's at equilibrium. So the acceleration, and we have 1 minute and I'll be done. The acceleration is going down, right? Now you want to think about that. It is accelerating. It is speeding up, but at a lesser and lesser rate as it comes in. That's a little bit new and interesting. But so now look, now it finally asks, what's the jerk doing? What's the change in acceleration doing? I might not otherwise have known that. I've never really thought about that before in Physics 203. But if I look at this pattern right here, it seems pretty straightforward to conjecture, and it is correct to conjecture, that if this pattern is continuing, the jerk must be going up. And indeed, the pattern does continue, and the pattern continues forever. There is no derivative here that is constant. Unlike everything we did in Physics 203. That's why we're spending a long time on this. F equals negative kx is a simple equation, but the implications are vast. This thing is an infinitely differentiable type of motion. Very interesting to me, but we'll leave it at that. That is class. I'll see you tomorrow at 12:15. I will hang out for a second. If there's any questions or any issues, I'll post this. Obviously, there's no new homework. You've been a delight as always. Bye, Chef. All right. Thank you. Have a great day, and I'll stop the recording. This class, I really do. And Felix loves it too. Thank you. Okay. Thank you. I'm stopping that.